we're going to use the lab material that's on GitHub. Okay. So we have lab 3-2 harmonic oscillator. In this notebook, I prepared a rudimentary example of high torch implementation of PIN and its application to harmonic oscillator. There are also some helper functions that I defined for you. If you're first time, seeing Python and things like that, don't worry too much about the part that I prepared for you. So especially the first cell that I'm running right now is comprised of functions to display the prediction results, create animations, and things like that. And those are not the ones that are critical. So you don't have to worry about it if any of the syntax doesn't make sense, but you can just move on. Harmonic oscillator, I mean, we already explained the theory, so I'm not going to go any deeper into that, but we're going to use a slightly different formulation. So instead of an mx dot plus cx dot plus kx equals to 0, we're using this this representation where instead of m, c, and k directly, we define zeta, which is c over 2 times square root of m times k, and then the omega 0, which is square root of k over m. The reason why we were doing this is this has a better physical meaning. So this equation, after you substitute the the zeta value and the omega value, it's exactly the same equation as the original mx dot plus cx dot plus kx. But in this way, we have a better physical meaning where omega 0 is what's called the angular frequency. And then the zeta is the damping ratio. So when zeta is 0, what's going to happen is, the spring damper system will not have any, friction. So that once you pull the spring and let it go, it'll vibrate forever. And then omega 0 is actually what controls the frequency. So when omega is large, then it's going to, vibrate faster. When omega is small, then it'll not, vibrate, very fast. So in that way, we have only 2 variables representing the entire system as opposed to the original 3, M, K, and C. Another thing is that in terms of the damping ratio, zeta, usually we consider 3 different situations. When zeta equals to, when zeta is greater than 1, which means the damping is pretty large. And when that happens, if you pull the spring and let it go, instead of vibrating, it'll just slowly restore back to the original position. Okay. When zeta is lower than 1, then there's going to be a little bit of vibration. And the extreme case is when zeta is 0, which then the vibration will continue forever. And then some value in between 0 and 1 is going to give you a vibration at the beginning, but then it'll slowly slow down and then go back to the equilibrium state. And then the threshold between the zeta greater than 1 and zeta lower than 1 is the critical damping, where this is kind of the configuration where the restoration is going to be the fastest, yet the vibration is not there. So the moment you pull the spring and then let it go, then it'll quickly go back to equilibrium, and then nothing's going to happen. In our case here in this demonstration, we're only concerned under damped scenario. That's the fun part. actually. If it is over damped or critically damped, then nothing interesting happens. So we're going to only consider the under damped scenario. For the scenario where the under damping happens, this is the analytic solution. Again, if you're not a mechanical engineering major, you don't have to memorize this. I just listed here so that you have a formula for the ground truth, so that later when we have a prediction, we can compare it against the ground truth. Now, right below this, you'll see a code that is to determine the zeta and omega. It's called the determine coefficients. Again, this is a helper function that I defined. So if this doesn't make sense, don't worry. All it does is to take inputs, which are x, zeta, and omega, where x is the initial condition. So initial position and the initial velocity of the system is one of the inputs for this function, as well as the zeta and omega. And given those parameters, what this function is going to do is to determine the amplitude and the phase for the ground truth over here. So if you look at the ground truth, we have a times exponential of something times sine wave, right? So a is the amplitude, okay? If you have a bigger a, then you have a, in general, larger vibration. If you have a smaller a, then you have a smaller vibration. And that amplitude will decay. So exponential of negative of something times t, right? So it'll go down, right? And then we have the sine wave. Oops. We have the sine wave. And then the frequency is determined by the omega 0. But here's the phase offset. So this code is essentially just code for determining those a and the phi, the phase parameter, so that we can generate a ground truth. Again, if none of this makes sense, don't worry. That's just there to set up the ground truth and all that. So here, we consider the initial condition where the initial position of x, initial displacement of the mass is 1, and then the initial velocity is 0, okay? You can feel free to change this later to something else, okay? Here's another, thing, omega 0. Here we consider 2 pi as the angular frequency. But again, later you can play with this by changing it to a larger value, smaller value, so on and so forth. Zeta damping ratio, we have 0.15 as our initial condition. Of course, you can change it later, but make sure that this code only works for under damped scenario. So zeta needs to be more than 1. Can be equal to 1, by the way. Now, the rest is the code for generating the ground truth based on those parameters. So let me actually, there we go. So for that particular setup, this is kind of what, we get. So initial displacement is 1. So that's the stretch of the spring. And then the spring goes down, up and down, up and down. But then the amplitude kind of decays. And then, it's always a good idea to, get a feel of, how things change. So instead of 2 pi, if I change it to 5 pi, then obviously we'll have much more frequent vibration. And then if zeta is greater than, the initial set, let's say 0.8, then obviously the damping is much weaker. Much stronger. so that the vibration is almost not noticeable. So it starts from 1, goes all the way to 0, but there's a little bit of overshoot. If I reduce it to 0.01 or something closer to 0, then the decay of amplitude is almost negligible. Now the vibration goes on and on, right? So that's kind of the problem we have. Oh, and of course, the initial condition, this could be 1 or 10, but also you can have an initial velocity. So in this case, now I set to 1 and 1. So the position is 1, and then there's an upward velocity, right? And because of that initial upward velocity, you can see that, actually, let me give a bigger velocity. Yeah, so because of the initial upward velocity, now when you let the spring go, it goes up first before going down, but then the rest of the process is pretty much the same, right? So this is, what you can play with. But again, I'm going to revert it back to the original setting. And this is the dynamics that we're going to try to learn. Okay. Now, that's the ground truth, right? Based on the formula that involves exponential and sine, right? Because for this particular system, we know the ground truth, like analytically, we can calculate the analytic solution of this. But for most of the time, in the real world physics, there's no analytic solution. There's no ground truth, right? So we're going to emulate that situation by sampling some samples from the ground truth. So what's happening over here is we're sample points from the first 1.2 seconds. Okay, so we're going to assume a scenario where we make an observation for the first 1.2 seconds. And then from that observation, we're going to train our model. And then after the model is trained, we're going to see if we can predict beyond 1.2 seconds, because model has never seen beyond 1.2 seconds, right? So T max sample is the maximum time for sampling the training data set. So I set it to 1. And then the sample stride is 20. So the stride is basically the sampling frequency. So, sampling, the opposite of the sampling frequency. So when the sample stride is 1, which is the smallest value that you can have, then we're going to create a really dense sample. And then some large number will make it a little make it scarcer. Now, this is the part. So we have the ground truth. Oh, actually, this is something I forgot to mention. The ground truth that we generate over here is basically it's basically an n by n/1 tensor. Okay, that's GT. N/1 tensor, where n is the number of time steps. Okay, so for this ground truth, we have total of 3 seconds of simulation. And then that 3 seconds of simulation, we have total 1,000 steps. So that 3-second interval is divided into 1,000 pieces of small chunks. Okay. So delta T is 3 divided by 1,000. So from there, we're taking the sample. So, we're going to take the sample of the position, and we're also going to take the sample of the time domain. And that's how we, construct the training data. So for training data, we have, some n by 2, where n is the number of training samples, and then 2 corresponds time and the position. So if I run this, then it'll visualize where the training data was sampled. Again, this is a toy example, so we don't have a whole lot of training points. But this is kind of emulating the real world scenario, right? So we make some measurement initially, and then from there we want to know if the model can predict the future. So far, so good. Now, now that we have the data prepared, the rest is really what you already know. Okay. So the first thing is we're going to create a machine learning model. So in this case, we have a neural network, which I named the backbone. The backbone neural network, this one is exactly the same as what we saw in the lecture slide. So we have two hidden layers in the middle, and then we have the input layer and then the output layer. So we have a neural network with 4 layers. The input layer, we have 1-dimensional input, which is the time t. And then the output layer, again, we have 1-dimensional output, which is the position x. Okay. So what this neural network does is to take a time t, spit out the position, make a prediction of the position. That's all it does. Now, in between, we have 2 hidden layers with 32-dimensional feature vectors, or 32 hidden neurons each layer. So that's how the model is constructed like this. Now, if you look at the forward, this is where we stitch things together. So we saw this yesterday, right, during the PyTorch session. As you can see, the fully connected layer, the input layer takes input x and then spit out a 32-dimensional feature vector. Here, we use a thing called a SILU. Okay, SILU is a variant of an exponential ReLU. So exactly because of the conversation we had about ReLU being, like ReLU derivative being 0, we're using SILU. And SILU is kind of exponential approximation of the ReLU, sort of. And since that one involves the exponential function, it'll be differentiable infinitely many times, right? So we're using this activation function instead of ReLU, but that's essentially what it is. And then we have a boring repetition of the same thing, right? And then actually before the output, I don't know why I put this over here. No worries. Okay, yeah, this is correct. So after a few repetitions of perceptron activation, now we have the final output. And that's essentially how our model is defined. So if you want to print the summary of the model, you can see that by doing print model, right? So nothing new here. Now, as the first thing, what we're going to do is to train this neural network without any physics-informed loss term to establish the baseline, right, in terms of what the neural network can or cannot do. Again, here's another helper function. I should have actually moved this to the top, but this is where the training happens. If you did the homework, if you did follow the lecture yesterday, this should automatically make sense now. Okay, so we have a PyTorch optimizer with Atom. We have the learning rate and the model parameters over here. There are, in between, there are code for saving the progress, but we're not going to worry about it in this class. We have total of 30,000 iterations, which might be a little too long. So I'm gonna, for this class, I'll make it maybe 3,000, so 10 times shorter instead of 30,000. Now, inside of the for loop, I mean, we're basically doing the same thing. We set the gradient for the optimizer to 0. That's always the first thing to do, and then make a prediction. And then using the prediction, you compute the loss, which in this case we're just comparing the prediction with the ground truth label. The name of the variable is a little misleading. Output is actually the label, the ground truth. And we're computing the square of the difference between the two and then take the mean. So it's a mean squared error is how we define the loss function. And then from the loss function, we do the backward, so back propagation of the loss function. And then the optimizer will catch that and then make a progress. So this is something that we saw already yesterday. And basically, that's what's going to happen. And then the rest is for plotting and generating animations. And in fact, let me pause this. Let me pause this and then change one line. Now, every 1,000 iterations, it's going to plot the progress. So this is, the blue line is the neural network, after 1,000 iterations. It fits pretty well on the training data, not as much. But then as you go beyond that, training data, it's completely off. It's just off to the moon. And then after 2,000 iterations, the situation is a little better. But again, after the, t equals to 1.2 seconds, it started to be, way off. Now, after the 3,000 iterations, as long as the training data is concerned, it's pretty accurate. But then beyond that, it's completely off. Feel free to train longer. If you train longer, you will see that the blue curve is going to fit almost exactly, through the training data, which is great. But then, beyond that time point, the neural network will just decide to do nothing. And then you're going to see something like this. So as a physical model, this is horrible, right? This is a very inaccurate model. For the time interval that you already seen, it's going to do a great job of at least interpolating the training data. But then beyond the point that you've never seen, beyond the time that you've never seen, then it's not going to be able to predict the position of the harmonic oscillator at all. Okay. Yes. In general, yes, but again, for a physics application, what's the use then, right? You make only 1.2 seconds of measurement, and in between 1.2 seconds of measurement, yes, you can use it as an interpolation algorithm. For example, because of the delta t, we don't have the data in between. The nice thing about this neural network now is that you can evaluate the positions in between those data points. But again, as you go beyond t equals to 1.2 seconds, then it's not going to extrapolate. And maybe from I don't know, from other machine learning applications, that might be okay. But for our application, which is to predict the physics, this is not okay. We want to be able to generalize beyond 1.2 seconds. So this is where GIAN comes in. By the way, yeah, so actually a lot of the training code is devoted for generating this animation. So that's why the for loop is a little longer. So you see that crazy thing that the neural network is doing. Now, this is the version with the physics-informed loss term. And pretty much everything over here is the same except for this line. So this line over here, what's happening is we evaluate the model and then we make prediction, okay? And for that prediction, we're doing torch.autograd.grad to compute the dx, okay? And then on the dx, we compute the torch.autograd.grad to compute the ddx, the second derivative. And then, the syntax of the autograd.grad we already seen, so hopefully this makes sense to you, right? And after we evaluate ddx and dx, we compute the residual. And the residual is ddx plus 2 times zeta times omega 0 times dx plus omega square times the x, okay, is how the residual is defined, which is exactly the governing ordinary differential equation that we saw before. And that residual squared and then compute the average is what we define as a physics loss. So now that you know the PyTorch, autograd, and everything, PIN is nothing more than, right, the same exact network, this auxiliary loss function term, which gets added on top of the data loss. The data loss is the usual MSE, mean square error. So data loss plus the physics loss is what defines the total loss. And PIN is nothing more than just that, right? And then what we're going to do is to do the loss stop backward. And when we do that, now since the loss term contains not only the MSE, but also the residual of the ODE, the weight updates are going to happen in a way that the model will somehow respect the differential equation describing the harmonic oscillator. Sorry? Oh, this I will explain later, but this is to avoid the physics loss and the data loss fighting against each other. Yeah. So this is something that we still have to discover, and we're not done with the PIN lecture yet. So we're actually going to talk about that on Monday. But to give you an idea, if you don't set this number, I mean if you don't set the significance of this term, lower, then the physics loss term and the data loss term will fight against each other, and then it'll never converge to any meaningful solution. So that's why we will multiply 0.111, sorry, 0.0001 in front of the physics loss. And in that way, initially, the physics loss gets multiplied by some really small number, and then data loss is going to be the predominant loss function term that will derive the entire search process. But then as the data loss gets smaller, then physics loss terms start to be more dominant, right? And then that's essentially what's going to happen. Sure. So physics laws, okay, yes, in terms of the units, they're different, right? Data loss is evaluated in the space of the displacement. Physics loss is evaluated in the space of force or acceleration. But the objective function is to reduce both of them together. So physically, adding the two may sound a little weird, but mathematically, from the perspective of optimizing the two terms together, there's no problem with that. Doesn't matter. Here's one chunk of computational graph. Here's another chunk of computational graph, right? And then no matter how complicated they are, at the end they're combined. Now, a gradient operator is linear operator, which means the gradient of the sum is the same as the sum of the individual gradients. So that's, essentially it's an addition of the gradient. Mm-hmm. Mm-hmm. Which is still fine, as long as you can take the derivative of the loss with respect to model weight and bias. That's all you need. Where those gradient come from doesn't really matter, right? So you have two chunks of graphs that involves both, WMB, right? And then they get combined at the end to the back propagation. Eventually, you get the derivative of loss with respect to the, weight and bias. So yeah, it's the same deal. Other questions? We're still running this cell. I did not reduce the maximum number of iterations, so it's gonna take a while. So if you have more questions, feel free to ask. Um, it's yeah. I mean, you can change the DPI, which can be done by figure dot. So yeah, there's a way. I can tell you after the class if you need. It's plt dot figure and then fixed size, and you can specify the DPI. Yes. So this is something that we haven't covered yet. For now, let's say collocation points are just the points where the PD residual or the ODE residual is evaluated. So we're evaluating the physics laws at separate locations than the training data. Okay. For more details about the collocation points in terms of how we select them and so on and so forth, we'll talk about that on Monday. So graphically, this is kind of where the collocation points are distributed. Okay, so we are distributing the collocation points across the entire time interval, and then on the collocation points we do not know the positions per se. We do not know the positions corresponding to the collocation points, but we do know the PD residual, the ODE residuals, right? So that's where we evaluate the residuals. And then, the training data is training data. It's the same thing. And, here we have the iteration 10,000. No, I said collocation points. We do not know the position. We do not calculate the residual. Remember, physics informed laws, we're not computing the actual predicted position. We're at the collocation point, we're only computing the residual of the PDE, not the positions. Okay, so we're only evaluating the derivatives at the collocation points. And again, remember, at the collocation points, we do not know the actual value of X. Okay, so these points are just graphically there. We're not fitting, for example, the blue curve onto the green points. That's not what's happening over here. The green points are graphically there to tell you where the collocation points are located. All right. So let me finish explaining this, okay, and then we'll talk more about what's really going on. So one noticeable thing is that at the iteration 10,000, we already have a pretty good result over here. So unlike the previous case where the blue curve sort of deviated, now we have the blue curve kind of following the black line quite well, the ground truth very well. And then if I plot this in an animation, it may take a well, yeah, you can see that at the very beginning of the training, the model is focused on fitting to the training data. So here we go again. You see, the training data is almost immediately fit, and then the rest of the time we're adjusting the graph shape, and that's the role of the physics informed loss term. And now that we have this model, what we can do is to hold on. What we can do now is to make prediction beyond the time 1.2 second, right? And then use it as kind of a surrogate model without actually having to run the simulation is kind of the idea here, okay? All right. Do you know what the residual is? Do you do you know do you know the term residual, first of all? What is the residual? Do you know the meaning of the term residual, first of all? Do you know the meaning of the term residual? Yes. Do you know what residual is? Residual of an equation? No. I think that's where the confusion comes from. A residual of a PDE or ODE, remember, actually, let me go to the, so this is our ODE. And what we're doing is to approximate the function x. Remember, x over here is not a single variable, it's a function over time, right? So x is a function that takes time as an input and then spit out some value, which has a physical meaning that, the position of the mass, right? So we're approximating the function x using a neural network. And the neural network that we're using to approximate this function x is not the same thing as the original function x. So the x, the real x, okay, that correspond to the ground truth dynamics is unknown. And we're approximating that using an artificial neural network. If that approximation is perfect, meaning the neural network is exactly the same as the ground truth, then when we put this into the equation, the value on the left-hand side should be exactly 0. However, our approximation of the function x is not exactly the same as the target function x. So there's a difference between the two. And because our neural network X is not exactly the same as the ground truth, the left-hand side, this term over here, not be exactly zero. So, instead, this part will have some weird value. And that weird value is what's defined as a residual. Yes. It's not the same as comparing position to position. Okay. Comparing position to position is the data loss. And we define that on the training data, which are the yellow points. But for collocation points, for physics informed loss, what we do is to simply evaluate this equation. We don't really care about the actual position X, but the evaluation, the left-hand side of the governing equation, and we measure how much it deviates from zero is what is defined as the residual. And we're trying to minimize that at the collocation point. So if I go back to the quote and the plot over here, so that's what I mean. For the yellow dots, we're measuring the value to value difference. Okay, so the position at time t equals to, let's say, 0.2 was about 0.75. And then let's say the neural network initially, made a wrong guess and said 0.9, right? So then there's a difference between the two. And that will give a penalty, right, in the training loss function. And we'll try to minimize it. So now we have, the value, pretty close to this. But at the collocation points, the green dots, we're not actually doing that. Instead, at the green dots, we're simply taking the derivative of the neural network and then, put that derivative in the neural network, make sure that the mx, mx dot, mx double dot plus cx dot plus kx equals to 0. Okay. And again, because the neural network is not, perfect, that, mx dot, double dot plus cx dot plus kx is not going to be exactly 0. It's going to have some values. And that is what's being minimized. Now, if you think about the real world scenario, this kind of makes sense. For us here, since the harmonic oscillator is such a simple system, you may wonder what's the point of doing this. But imagine instead of a harmonic oscillator, let's say you have some expensive fluid simulation. Okay. So you have some, instead of the spring mass damper system, let's assume that you have some expensive fluid dynamic simulations. You can only afford a very scarce simulation for the first 1 second, but then you're interested in a longer term prediction of the fluid system. If you're a CFD guy, without knowing PIN, what you can do is to just run more simulation, wait a few more weeks, and then finally you get simulation all the way up to time t equals to 3. But the good news for you is that, okay, you have, simulation data up to 1.2 seconds. But since you're working on a fluid system, you know that the fluid system is governed by what's called the Navier-Stokes equation. And the Navier-Stokes equation, even though you don't know how to solve Navier-Stokes equation, right? And there's no way you can solve it by hand. Even though you don't know how to solve the Navier-Stokes equation, you can still, similar to what we've done, you can still evaluate the residual of the Navier-Stokes of my neural network at any time location t in this interval. Correct? It's different than evaluating the actual fluid velocity, fluid pressure, all that kind of stuff, right? If you were to actually predict, compare the difference between the pressure, velocity, and things like that, then you will have to run the simulation all the way to time t equals to 3. But even without knowing the actual values of pressure, velocity, and things like that, you can still evaluate the, the residual of the Navier-Stokes equation by simply taking the automatic derivatives and then plug that into the Navier-Stokes equation. That makes sense? Yeah. Yes. They don't coincide. Yes. For yellow, you don't need to get the derivatives. For yellow, you just need the prediction of the neural network, and then you already have the ground truth. Just compare them, point to point is what's happening at the yellow points. Yeah. Yeah. Other questions? Yes. Yes. So what? Sorry, what's your question? Yeah. So this is. Oh, yeah. So this is X. This is X predicted by the model. This is the model. Yeah. And then this is the derivative of that. Maybe that's a typo then. Where? Yes, the neural network X is substituted here. So we're evaluating again dx dt at the collocation points. We're evaluating X at the collocation point, dx dt at the collocation point, ddx dt square at the collocation point. All three of the terms involving X. Okay, this, and this. No, all three of them. Right. So okay. No. So we evaluate, okay, X at the collocation point. So far, so good. And then we take the derivative of that with respect to the collocation point T and calculate dx. So the time derivative is evaluated at the collocation points again. The second derivative again is evaluated the evaluated at the collocation point again. And for those three terms, x, x dot, x double dot are used to evaluate the residual. So I wouldn't call this a predicted value or anything like that. We're not comparing predicted value to a predicted value. We're evaluating a sequence of position, sequence of velocity, sequence of acceleration. It's a function that we're evaluating. Okay, so x is a function, dx is a function, dx is a function, and those functions are plugged into the ODE. And if those three functions are accurate, then you will have no residual equals to 0. But since they're not accurate, this will have some value. And therefore, when we define the physics laws like this, which is the residual square of a mean, then you will have some positive value over there. And then, we're basically, minimizing that during the training process. The difference between the actual function versus the approximated function by the neural network. All right. Okay, so in this way, the caveat here, the main takeaway message here is that even if your training data is available in certain interval of time, or later on when we talk about PDEs, partial differential equation, even if your training data is available at certain spatial locations, limited spatial location, it doesn't matter, because collocation points can be evaluated anywhere in time, anywhere in space. You can distribute, you can scatter as many location points as possible, right? And then over there, you don't really need a training data. You just need to evaluate the residual. And evaluation of the residual can be done without knowing the actual value of the position or actual value of the physical quantity. And in that way, you can train a neural network. And once the training is done, then you should be able to make predictions outside of the area where the training data is available, is kind of really the main takeaway message here. So that's the first part for the pin. Now, at this point, I'm not sure if it is a good idea to go into the second part, but here's a different use of pin, which is to pretend that we only have the training data, but we do not know the omega and zeta. So in the previous scenario, we had omega and zeta given, and we wanted to predict what's going to happen in the future. But instead, you may also think of a situation where you're an experimentalist and you have a spring and damper system. You let it go, record the trajectory using camera. You collect all the data, but you don't know necessarily what omega is, what zeta is, right? So in that case, pin could also be used to figure out the values of omega and zeta. So that's the second part, which is called the data-driven discovery. So the first part that we just saw is the solution of a given differential equation. So pin can be used for solving a differential equation to find the solution function like that. But pin could also be used to discover the equation itself. Okay. But I guess for this one, we're going to come back on Monday and then take a look into. So for you, I guess the valuable thing to do is to go back and then the code where you change the angular frequency and the zeta. See if you can make the problem much more interesting. So for example, the best way to make this problem more interesting is to increase the angular frequency and then reduce the damping. So in the simulation community, we call it a stiff system. And stiff systems are harder to simulate. So now instead of the original 2 pi and 0.15, now we have a crazier looking, um, you know, system over here. And then obviously, if you, try to, um, sample data from here, this may not be enough, right? And then, try to train the model in that case. Well, let me explain this first, and then I'll get back to your question. All right. So now, I'm training the same model, but with a different physical conditions. And the bad news is this code is not going to work very well for that tougher situation for an obvious reason. So you may want to increase, for example, the number of training samples. You may also want to make the architecture more sophisticated. Right now, we have 2 hidden layers. Each has 32 neurons. You may want to increase the number of neurons. You may want to, make it deeper. Go ahead and experiment. Okay. What else? You may also want to play with the optimization in general as well. So there are a lot to play with this added complexity. So try to have fun, over the weekend, and then on Monday, before come back to the class, try to have fun with different configurations, different physical parameters, and then see if you can train a model that gives you a better result. Don't be too ambitious though, because pin is limited. So if the stiffness of the system goes beyond certain point, pin will fail to learn anything, or it will still learn something, but it's not going to be accurate. So don't be too ambitious, but try to change, increase the complexity of the model a little bit. Yeah, see, it's already struggling. Yeah. So this is dramatically different result, right, compared to the previous one, and that's because we have a really stiff system with a really high angular frequency. So don't be too ambitious like this, but change the physical parameters and see if you can manage to train your model. With the complex problem, I think you're going to need a more frequent sample. Of course, you're going to need more sophisticated model. But using those, see if you can train the model and then have fun with it. Okay, so that's going to be the homework. Back to the question: how to determine the number of samples? Well, this is we're emulating the real world scenario. There's no way of determining how many samples you need or how to sample the training data. Like in the Navier-Stokes situation, pins are usually used without any simulation data. They only have the initial configuration of the fluid, which means that you have only one orange dot. You have an orange dot at the beginning, and then starting from there, you try to fit the curve without having the additional training data. So usually the data points are given by the problem. It's not something that you determine. Yeah. So if you can afford a large number of data, good for you, right? If you can afford, for example, if you can afford a large number of data all throughout the interval, then you probably don't even need pin, right? But in most of the cases in the physics world, you can only afford a very short period of time at the very beginning, right? Um, Yeah, yeah. So those are the things that you should play with. But again, this is only the emulation of the real world situation. It's not like to train pin. It's not like you got to have certain number of training data. Okay, so you have to live with what you already have. So in this case, um, you know, this is a very unfortunate scenario where, right, the training data is not enough to resolve the frequency actually. So, um, I don't think the pin will ever be able to learn from it. But again, this is not the sampling rate is not designed for this high frequency data. So um, no, I changed both damping and the angular frequency. So that is something that we're going to see as the limitation of pin. In fact, if the initial condition, boundary condition, or physical parameters change, then you have to retrain the model. Yeah, which to me is kind of a dumb, thing to do. But originally, when the authors first came up with pin, they came up with it as a solution, as a solver for partial differential equations. So solving Navier-Stokes equations using the traditional numerical solver will take forever, but you could also solve Navier-Stokes equation using neural nets, and that tends to be much faster. Again, for harmonic oscillator, solving the harmonic oscillator equation using numerical solvers will be like a second, less than a second, versus training this takes, more than a minute. So it kind of beats the purpose, right? But that's because I, got this toy example. For more complicated examples where, solving the equation takes much longer, then, training the neural network is probably, better deal computationally. So similar to what you would do with the traditional physics-based solvers, when you have different initial condition, different boundary condition, different anything, you'll have to run the simulation again, right? So whenever something changes, you run the simulation again, change, simulation again, right? And each simulation takes 4 hours or a day or whatever, right? Now, with pin, what happens is the same, exactly the same. You change the physical parameter, change the initial condition. You have to solve it again by doing the neural network training, and then at the end you will have a solution. So that we're gonna see later. So right after this is a different method called a neural operator, and then there's also a method called the physics-aware recurrent convolution. Those are the ones which can actually learn and predict instead of solving. So for those methods, what you can do is whenever the initial condition or the physical parameter change, that can go in as an input to the neural network, and then the neural network will just spit out the predicted outputs. Yeah. So there's a slightly different nuance in terms of what physics informed neural networks do. To give you a background, pins are developed by applied mathematicians, essentially. So those are the mathematicians who came up with this idea of solving PDEs using neural network, which is why it's a little bit different from our perspective. The engineers were always, thinking from the perspective of, okay, what if I change this variable, right? What if I change this physical parameter? What's going to happen? What's going to be the response of the system, right? And that's something that we're interested in doing. Mathematicians, they're looking for a different algorithm to, solve a PDE, right? Right. Fourier could be one way of solving PDE, right? Or you could also do finite volume method, finite, right? So neural network as another solution method for PDE, they come up with this. And us as an engineer looking at this have a lot of question marks. Like, what the heck is thing, and what's the use of this in the real world scenario? And I think a lot of questions today are kind of coming from that perspective. But we'll get to the point. We'll get to the point where we can train a neural network, more practical engineering application, where okay, this whole black box, whenever you throw in an input, initial value, it'll just predict, what's going to happen in the future, as a function of those initial conditions. That will be far more useful for many of the engineering applications, right? So we're going to get there. But to get there, you got to know this first. And then once you know this, then everything else is going to be, pretty straightforward. So, all right. I think we're way over time. So thank you all. And on Monday, we're going to, go back to PIN. There are actually many other, slides that we still have to cover about PIN. And then there are applications of PIN. And once you take a look at those different applications, I think it will start to make sense a little more. But before coming back, like I said, play with the code, and then see what you can find. So thank you so much. Have a great weekend, and see you on